Hello physics students, it's Dr. Brinzy here, and this is the first of a series of videos that I want to show you about solving problems involving Newton's second law and forces. The reason I'm making this series is because I want to show you what all of these different types of problems have in common. They have a common way to approach them. So I want to show you what they all have in common so that when you attack any sort of problem involving forces, you could even throw things like pulleys in there and stuff like that, then you will have enough confidence to know that, hey, I can follow this kind of like series of steps and I'll be able to still solve that problem, even though it looks different than other problems that I've solved before. So let's start off with this problem, and this will be the simplest of the series of problems that I'm going to show you in these videos. We have an 8-kilogram block is pulled horizontally across a table by a rope. The coefficient of kinetic friction is 0.2. What is the tension in the rope if the block accelerates 3.0 meters per squared second? Before we actually solve this problem, I want to tell you what steps I think of when I solve any type of problem involving Newton's second law and forces. The first thing I do is I want to draw a sketch. That's a good thing to do for any physics problem, especially one that doesn't have a sketch provided to me. The second thing I want to do is I want to draw a free body diagram. A free body diagram, you know by now, is a diagram that shows the forces acting on an object of interest. The third thing we want to do is we want to place the positive y-axis along the normal force. Now that might sound, you might not actually know why we actually do that yet, but when we get into problems involving inclines, that will become pretty clear why we actually put the positive y-axis along the direction of the normal force. The fourth thing I like to do is, actually not that I like to do, but we have to do this, is then we have to break any forces down into their components along the x and the y-axis that we've chosen. The reason we need to do that is because right after that we need to write Newton's second law, F net equals ma, for each of those two axes. And if I have a force that doesn't point all along the x or all along the y-axis, then I'm going to have trouble with step number 5. Finally, after we've written down Newton's second law for each axis, then there is a system of equations that we're going to need to solve. So this is the 6-step process that I like to use to solve problems involving Newton's second law and forces. So let's apply the 6-step process to this problem that's been presented to us. First thing I want to do is I want to draw a sketch. So as I read through the problem here, it says an 8-kilogram block, and so that sounds like that is going to be the object that is of interest to me. So I'm going to draw an 8-kilogram block right away. And then once I've drawn that, I go ahead and go back to where I left off. It says it's pulled horizontally across a table by a rope. Okay, so I'm imagining this 8-kilogram block sitting on a table, and it's being pulled horizontally by a rope. Horizontally means along this direction. It doesn't tell me which direction, it doesn't tell me left, it doesn't tell me right, so I get to choose, and I'm going to choose being pulled to the right. Okay, now that I have that new information in there, I continue reading the problem, starting off with the next sentence here. It says the coefficient of kinetic friction is 0.2. Okay, well, coefficient of kinetic friction. Well, that tells me that there's friction acting on the block, between the block and the table. And if you remember, the coefficient for kinetic friction, we give this Greek letter mu to the coefficient of friction, and we put a little k down there to tell somebody that it's kinetic, in other words, it's moving friction. If you don't remember where this came from or where we would plug this in, the formula for calculating the amount of friction force is given by this formula right here. The force of friction is equal to the coefficient of kinetic friction times the normal force. So they've given me this, and I'm guessing that I'm going to need to use this formula to figure out some friction force, and I can already tell that I'm going to need to know a normal force too. Okay. It says here, what is the tension in the rope if the block accelerates 3.0 meters per square second? So it's asking me for the tension in the rope. Oops, I forgot to write down my friction force there. What is the tension in the rope if the block accelerates 3 meters per square second? Okay. So now that we have a sketch, let's draw a free body diagram. And I'm going to move this sketch onto the next page. Everything that is in the text here is now in my sketch, so I'm going to actually create a new slide. And I'm just going to include the sketch instead of the text. That'll give me a little more room. Alright, so this is a sketch I just drew. And to figure out a free body diagram, first of all, I have to ask myself, what is this block interacting with? And then what's the force or forces that come as the result of that interaction? Well, the first thing that this block interacts with is Earth. And that, let's see, do I put forces next? No. Another thing that it interacts with is the table. Okay, it's in contact with the table. And then finally, the third thing that it's interacting with is the rope. So it has three things that it's interacting with. Now that I've listed everything that this block is interacting with, let's list the forces that come from those interactions. Well, Earth produces a gravitational force. The table actually produces two types of forces. One is a normal force, and the other is kinetic friction force. And then finally the rope, its interaction produces a tension force on the block. Okay, now that I've identified all of these forces, these are the only four forces that should go into my free body diagram. So let's draw a little dot to represent. Let's draw a dot to represent the object, the block. And the first force I've already drawn on there is gravitational force, pointing down. Normal force is perpendicular to the surface that the block sits on, so that is going to point upward. The kinetic friction force acts opposite the direction of motion, and I could imagine if this is being pulled to the right, that my friction force is pointing to the left. And finally, the tension force, that is the force that is pulling it to the right, so that will act toward the right. The reason I drew these two arrows unequal is because I know that these are going to be unbalanced forces. That's what's going to cause this acceleration. Whereas these two forces are balanced, so I drew those with equally long vectors. Okay, so there is our free body diagram. Now the next step is that I want to point the y-axis, the positive y-axis, along the direction of the normal force. So this has to be my positive y-axis, which is going to make this my x-axis, and positive is to the right, so there's my positive x-axis and my positive y-axis. Okay, that was a pretty simple step. Now for the fourth step, I have to make sure that all of these forces in my free body diagram are either pointing along the x-axis or along the y-axis. If they're not, then I have to break them down. Well, it turns out that this force, that's pointing along the x-axis, that's okay. The normal force is pointing along the y-axis, that's okay. The friction force is pointing along the x-axis, I don't need to break that down. And gravity is pointing down, I don't need to break that down. So you might be asking yourself, why in the world do we need to go through a step? Well, what if, for instance, we had a force pointing in that direction, like this? Let me see if I can quickly draw a force. So let's say that we had a tension force pointing in that direction. Well, if I had a force looking like this on my free body diagram, it's not pointing purely in x, it's not pointing purely in y, so then I would actually have to break this down. And I will actually show you that in the next video here, but for now, I just want you to be aware that that's what we're checking for. We're checking to make sure we don't have any angled vectors like this in our free body diagram. And if we do, then we have to break them down. Okay. That was step 4, just checking to make sure that all these point along x and y. So let's go on to the next step. Let's write down F net equals ma for each of the axes. So Newton's second law, and we want to draw or write Newton's second law for the x direction and for the y direction. So for the x direction, F net equals m times acceleration in the x direction, and F net equals m times acceleration in the y direction. When I'm looking at the x direction, I only want to consider forces acting along the x-axis. So the forces that I need to add up to give me F net are the tension force plus the friction force, but the friction force points in the opposite direction, so I give that a negative sign, and all of that is going to equal mass times acceleration. Well, we were given mass and we were given acceleration. Mass, acceleration, so let's replace those. I also showed you a formula for friction force. That's this right here. So let's replace that as well. So we're going to have tension force minus coefficient of kinetic friction times normal force. That's what I put here. Equals mass times acceleration. I know the coefficient of kinetic friction, that's 0.2 that was given to me in the problem, so let's replace that, and this is as far as I can go in the x direction. Alright, so let's substitute some things in here for Newton's second law in the y direction. So now I'm considering only the forces in the y direction, and those forces are normal force and gravitational force. And since gravitational force is pointing down, I want to make this a negative sign. Now we can replace Fg with m times g, and I can replace m here with the mass, but I also know that this object is not accelerating in the y direction, so that's going to equal 0, which means this entire right-hand side will equal 0. So what I have here is Fn, normal force, minus mg equals 0. I know what m is. That's the mass of the block, 8 kilograms. G is 9.8. Now you might be asking yourself immediately, well, Dr. Berenzi, wouldn't you substitute negative 9.8? No, and here's why. The reason we put negative 9.8 is because we're telling somebody that gravity is an acceleration and acts in the downward direction. That's what that negative sign is for. It tells somebody gravity is pointing downward. Well, remember, when I substituted in for, when I wrote down the gravitational force, I already told somebody that it's acting in the downward direction. So I've already accounted for the fact that this gravitational force is pointing downward. So I don't want to actually replace this with negative 9.8. Because I've already told somebody it's pointing downward, so I just want to replace it with 9.8. Okay. Now, imagine that I accidentally replace this with negative 9.8. Then what's going to happen? We're going to get negative times negative, which is positive, which means this thing, we're telling somebody that this thing is pointing in the positive direction, and that means you're telling somebody that gravity is pointing up, not down. So once you give a negative sign down here, you've already told somebody it's pointing downward. Don't tell them it's pointing downward again, otherwise it'll actually be pointing upward. Okay, with that said, let's replace M and G, and we get 8 times 9.8, and let's evaluate that. So we have normal force equals 78.4, oops, sorry, normal force minus 78.4 equals 0. And it looks like that is just about as far as I can go in that direction with the y direction. I suppose I could have solved for normal force, but I chose not to do that. We're going to do that in the next step, which is solving the system of equations, step number 6. So I'm finally on to the last step here. You're always going to get a system of equations here when you're dealing with two-dimensional forces. Well, I shouldn't say always, but almost always. So we have to remember how to solve systems of equations. So I'm going to actually erase this part to give myself a little more room here. Don't erase that in your notes, please. And then we're going to finally do this last step over here, solve the system. Okay, so we have those two equations and two unknowns. Whoops, that turns up. Let me back that up. There are two different ways that you can solve systems of equations here. You can either choose to solve by a method called substitution, where you solve for one of the two variables, and then you actually replace it or substitute it into the other equation. That's one method for solving systems of equations. The other way to solve systems of equations is what's called elimination. And that involves actually adding or subtracting multiples of one equation to the other one. And that's generally, there are generally times when that is a good method, and there are other times when substitution is a good method. Well, it turns out that this system of equations is probably going to be better with substitution, because I notice that two of my equations, or one of my equations has two variables, excuse me. This one has two variables, but this equation only has one variable, so it's pretty obvious that I could solve this for normal force and then substitute it into here, and that will be the substitution method for solving this system. So let's solve this system of equations by substitution. So adding 78.4 to both sides tells me that the normal force of this block, acting on this block, excuse me, is 78.4 newtons. And now I can substitute that number into here. And so I have tension force minus 0.2 times 78.4 equals 24. And then, as you can see, I can go ahead and evaluate this and then add 15.7 to both sides, and I get 39.7 newtons. So the tension force in this block is 39.7 newtons. So we've used the 6-step process to actually figure out what that missing tension force is in this block. And in my next video, we're going to actually have a force, a tension force that is actually pointing in a slanted direction. So go ahead and watch video number 2 if you are interested in solving that type of problem. Alright, see you later. Bye.